Hello friends, today we will discuss about the effect of a dielectric slab on the capacitance of a parallel plate capacitor. I've used one shortcut way of writing it, PPC. So let us first of all make a parallel plate capacitor. We know that it consists of two plates having charge plus q and minus q on them, and this plus q charge, remember that they are distributed in the inner face of the left plate, and the negative q charge is distributed in the inner face of the right plate. Okay, and the charge on the outer face of a capacitor is always zero. Now let us insert one dielectric slab, basically which is an insulating medium, but that can be polarized. It won't let the charges to flow, but it can get polarized. That it can separate the center of positive and negative charges. Now we know, let us take a particular case when the thickness of the slab be less than the separation between the two plates in the parallel plate capacitor. It means, I mean to say, this T is the thickness of the slab, whereas D is the separation between the two plates of the parallel plate capacitor. Okay, now we know when the slab was not inserted, then also because of this plus q charge, this is high potential and there is a low potential, so there is a potential difference, and hence one electric field is set up inside the capacitor, parallel plate capacitor. Let me say that electric field as E naught, and that electric field we know always is directed from the positive plate towards the negative plate, the positive charge towards the negative charge. Okay, from high potential towards the low potential. Okay, now when this slab were not present, everywhere here the electric field was E naught. Everywhere the electric field was E naught, everywhere. Okay, now the thing comes is, due to this positive charge, by the principle of induction, in unequal negative charge is induced towards the left face of the slab. Okay, and due to this negative charge, the positive charges are induced towards the right face of the slab. Okay, now due to this positive charge and negative charge, an electric field is set up there. I'll call it as induced electric field, or you can say it as internal electric field within the slab, and it is set up from, again we know that electric field is directed always from high potential to low potential, so this induced field is actually set up from right towards the left, okay, which is opposite to E naught. So can we say now that because of this field EI being induced within the capacitor, what is the net field induced inside the dielectric slab now? Definitely it is E naught minus EI, since they are in opposite direction. I haven't written here vector because it's not required. In fact, that is also true, but only this is the vectors are in opposite direction. Only the magnitudes can be written as the difference between the greater magnitude of the electric field minus a smaller magnitude of the electric field. If I denote this E net as E only, that can be written as E equals E minus EI. Okay, but one thing is known from the definition of the dielectric constant, or we call it as relative permittivity, that the electric field inside the when there was a free space over electric field in that medium, this equals to K. It means E equals E naught over K. Okay, now you can understand it like this also, that the net electric field inside the slab has decreased. In fact, no matter which medium you have kept except the free space or vacuum, the electric field when the medium is inserted is always going to decrease, and it decreases by a factor which is called as the dielectric constant. So E is always the net electric field inside a medium is the electric field when there was free space over the dielectric constant. Okay, so we'll remember it. We are going to use this expression. I'll name it. Now you say me one thing, because of the PD created between these slabs, the PD across the plates of the parallel plate capacitor is going to change because the electric field has changed. So PD across the plates of capacitor or across the capacitor. Okay, if I denote it by V, then definitely it is electric field into separation. You must remember one relation, V is equal to E into D. I can give you a Guru mantra to remember this. V is the potential difference, E is the electric field, D is the separation between those 2 points where the potential difference is V. You can remember it by with V is equal to E into D. This is the Guru mantra by which you can remember it, with V is equal to E into D. So I'm going to use the same thing, but the problem here is there are two kinds of electric field we have here. One is E naught, that is available within this empty region here, and another is E net, which is only E, that is available here. It's not EI. Try to understand. It's not EI. It's only E, which is the net field. If this slab were not polarized, then the electric field across the slab were this same E naught only, because this was available everywhere. Okay, so it's E not E naught. So now there will be E naught times T. Here in place of D I'll write T for, no, I'm so sorry, it's D minus T. D minus T. Where E naught is present, it's D minus T. Except this, everywhere E naught is present. Plus E, the net field in the slab, times its thickness or the separation, it's T. Okay, so I'll just rewrite this. Plus what is E? We know that it's E naught over K times T, and this is V. Okay, now we can take E naught common from here, okay, and then rearrange it. So when I take E naught common, I will get D minus T plus T over K. Okay. Now if we are interested in finding out the capacitance, then remember, we know in capacitor Q equals CB, then C becomes equal to Q over V. I need to find out the ratio of charge over the PD, the potential difference, to find out the capacitance of that capacitor. So I must express this electric field in terms of Q. I know the electric field in between the two parallel plates capacitor. This is plus Q and this is minus Q, and the charge densities are sigma, plus sigma and minus sigma. Then we have studied it before that there is an electric field because of this in the region between the two plates, and that electric field is given by sigma over epsilon naught. If you remember the derivation, because of this infinitely long parallel plate capacitor, the electric field was sigma over 2 epsilon naught, and because of this also sigma over 2 epsilon naught. And since the electric field due to each of the plates are in same direction, they will get added and the result will be sigma by epsilon naught. Okay, so I'm going to write that one, sigma over epsilon naught d minus t plus t over k. But sigma is, we know, the surface charge density, that's right, it's the charge per unit area over epsilon naught d minus t plus t over k. What is this? This was V. Now I was just required to find out Q over V, and that will only be equal to the capacitance. So Q over V will be Q over V. This term will go that side, so it will become A epsilon naught over d minus t plus t over k. This is my result for the capacitance of a parallel plate capacitor when a dielectric medium of thickness T is inserted, and we have seen that the T was less than D. Okay, now some cases arise here. What will happen if the thickness of the thickness of the slab is equal to the separation between the plates? Then the capacitance will become actually A epsilon naught over D minus again D plus D over K. Now these two D will cancel, and then K A epsilon naught over D. But we know that this K A epsilon naught by D, this is the capacitance of a parallel plate capacitor when there was no medium between the plates. It means it was the free space. So if I write it by K times C naught, then we have seen that the capacitance, if the entire medium is occupying, the entire space between the plates, then the capacitance will increase by K times. Okay, whereas the capacitance has still increased by inserting, but not by K times. But in this case, when it will completely fill the gap between the two plates, this one, when the medium will completely fill the gap between the two plates, it will increase by K times. K is the dielectric constant of that medium. Okay. Now one more interesting case arises here. What if metal is inserted? Metal is inserted. If metal is inserted, then we know for a metal the dielectric constant is infinite, which means the capacitance will be A epsilon naught over D minus T plus T over infinity. We know any number divided by infinity will be equal to 0, so it becomes A epsilon naught by D minus T. It's a very useful result, keep in mind. Okay. Now we'll move to number 2. Now we can discuss that how will the capacitance be affected if what I do is I keep the source connected and another source is disconnected before I insert the dielectric slab. What I mean to say is, how will the capacitance be affected when I am inserting a dielectric slab with the source remain connected with the capacitor and the source was disconnected to the capacitor? Okay, so let us see. Remember one thing, whenever source is connected, what is the work of the source? A source always helps in maintaining a constant PD across the load. Here the load is the capacitor. If the source is of V volt, let me say 10 volt, then what is the work of this 10 volt is to always ensure that there is a difference of potential of 10 volt across the two plates of the capacitor. This has to be a higher potential, let me say it as 10 volt, and this at lower potential, let me say at 0 volt, so that the difference should always remain at 10 minus 0 is 10. Okay, now I'll erase this. Okay, now Now, so what we understood here is when source remain connected, then the PD will remain constant. Remember this important thing. PD remains constant. The potential difference across the capacitor always remains constant because there is the source which will always ensure that the PD between the plates of the capacitor is always constant. Whereas when the source is disconnected, now definitely there is no source to supply constant PD. But one thing is for sure that the capacitor is not going to leak its charges through air. Hence, the charge will remain constant. Charge remains constant. Very important topic for CBSE. It means new PD will be equal to the original PD, whereas here new charge will be equal to the original charge. Okay. Now see how other parameters change. Now how about the capacitance? Let me say the new capacitance is A epsilon naught by D when there was no medium inserted. But we know that when medium is inserted, it has to be multiplied with K. So but this one is the original capacitance. So it's K times C. So definitely you have seen that it is also increasing. Here, the new capacitance will also be K times C because capacitance will always increase as it is directly proportional to the permittivity of that medium. So the permittivity of the medium will increase when we insert a dielectric slab in the capacitor. Okay. Now number 3, how will the charge change? So new charge is equal to, we know, new capacitance times new PD. The capacitance has increased by K times and the PD has remained unchanged. So C times B is equal to your original capacitor charge. So you have seen that the charge has also increased. Okay, charge has okay. Now how will the PD change here? Because charge has not changed, how will the PD change here? So V dash, we know V dash will be equal to Q dash over C dash, but Q has not changed and capacitance has changed, but Q over C will be equal to the original PD, hence it will be V over K. So this has now actually reduced. Okay, now fourth number, how will the electric field change? The new electric field, we know it has to be V dash over D. Distance definitely we are not going to change. V dash over D. E is equal to V by D or V is equal to E times D, weight. You can remember it by weight. V is equal to E times D. So V dash has not changed. D is not changed. So there is no change in this. And it's for sure that if the PD across the plates have not changed, how will the electric field change? But and from here we can see that it is not changing also. So number 4 here, how will the electric field change in this case then? E dash or E prime will be again V prime over D. V prime is V over K, we have seen it here, and V over D, and V over D is the original electric field. Hence we can see that the electric field in fact has reduced by K times. Now let's talk about, now we'll see that how will the energy stored in the parallel plate capacitor change. U, we denote it by U, and we know it is given by half of C V square. Now if we are talking about the new energy, it will be half of C dash and this is V dash square. Okay, so now how has C dash changed? It has increased by K times. And how has V changed when source was remained connected? It did not change. Hence it's V square. But we know that half of C V square, actually this term is the energy stored in the capacitor. So we have seen that the energy has again increased by K times. Okay, and here when the source is disconnected, can I write the energy as Q square over 2C. You know why? So that I can know that the charge is not changed, capacitance has changed. You could have done it by half CV square also, not a problem. So this is Q square, since charge has not changed, over 2 times the capacitance has always increased only, but Q square over 2C. This is again the initial energy and it has reduced by k times. So what we are seeing is that when the source is remain connected, the electric field, the energy, the electric field is not changing, but energy is changing definitely. Now come to 6 number. How will energy density change? I'll denote it by small u, and we must have derived it that it's half epsilon naught E square. But since where there is epsilon naught, a multiplier of k has to come. So it's E square. So this is new energy. Okay. But we know that in this case, since PD has not changed, the electric field has not changed. Hence, it's half epsilon naught E square. You can see that it is k times the original energy density. Whereas in the same way, you can see that the energy density will also decrease by k times, and it is evident from the fact that since energy has reduced by k times, energy density will also reduce by k times. Okay, so we'll keep the things in mind that whenever the source remain connected, the PD will not change, and whenever the source is disconnected, the charge will not change. After that, all the things will follow similarly. See, capacitance will always increase no matter what case has been given to me, and if PD is not changing, then Q dash will be only dependent upon the capacitance, and since capacitance has changed, definitely charge will also change on the capacitor. Here, since Q has not changed, then V dash will be dependent only on C dash, the capacitance. Since capacitance has increased and V dash is inversely proportional to capacitance, it will decrease by K times.